So now let's see the practical implementation of this. Okay, so let us say that I want to generate phi 1 and phi 2, okay, whose frequency is going to be some let's say 1 kilohertz, okay, or let's say let's say it's going to be 1 kilohertz. Okay, so let us look at this timing diagram here. This is my T clock, okay, and the periodicity of phi 1 or phi 2 is clearly 4 times T clock, because you're going through 4 states in 4 different clock periods, right. So this is my T phi, okay, which is basically the time period of both phi 1 and phi 2. There the duty cycle of the clock, T clock, is 50%. It's on and off for the same amount of time. On the other hand, the duty cycle of phi 1 and phi 2 is actually 25%, because phi 1 or phi 2, it is on only for one clock period and off for 3 of them, right. So the on by the total period is what we are calling as duty cycle. But it doesn't matter, right? The duty cycle, when you're talking of clocks, actually in digital circuits, the duty cycle doesn't matter as long as the periodicity is maintained, right? Because flip-flops care only for the rising edge, right? That's all that matters. So to a first order, we don't have to worry about the duty cycle, okay? But in any case, what you see is that T phi is equal to 4 times T clock. Okay, so let's keep this in mind, and then let's say this is T clock, okay, I'm talking of T phi, right. So let us say I want, so I'll put it the other way, this is T phi, right. Let us say I want T phi to be 1 microsecond, right. Then clearly, right, or in microseconds, and I'll write the same thing in frequency also, f phi, right. So if this is 1 microsecond, then this is going to be, no, I'll keep this as 1 millisecond for now, okay. Then this is 1 kilohertz, right. Then I know that T clock, okay, or f clock has to be 4 times that frequency, and therefore it has to be 4 kilohertz, okay. T clock therefore has to be 1/4 of a millisecond, 1/4 of a millisecond, which is 250 microseconds, okay. Now let us say instead of 1 kilohertz, I asked you to generate non-overlapping clocks which were 1 megahertz, okay. Then obviously this is 1 microsecond, okay, I'm talking of the output phi, right. Then f clock has to be 4 times that, and therefore this will be 4 megahertz, right, and therefore this will be 250 nanoseconds, okay. T clock is going to be 250 nanoseconds, right. Now in between I could also do, let me just move this down and add one more number, okay. So let's say I wanted to do 10 kilohertz, right. So 10 kilohertz is going to be 100 microseconds, right. This is going to be 0.1 into mega, so this is going to be 1 by 10th of a millisecond, 100 microseconds, yes, okay, and therefore this will be 100 microseconds, and this has to be 40 kilohertz, okay. F clock has to be 40 kilohertz, and the time period of the clock, the time period of the clock has to be 1 by 40 kilohertz, right. So what is that going to be? It is going to be 100 by 4, right. So this will be 25 microseconds. Okay. So what we see here is, as I start increasing the clock frequency here, right, the requirement on the T clock actually starts becoming tighter and tighter and tighter, right. So the point I am trying to make here is that if I asked you saying do it at 1 kilohertz, then your answer would be yes, you give me a T clock whose time period is 250 microseconds or a 4 kilohertz clock, and I'll give you the phi 1 and phi 2 that you asked for. If I asked for phi 1 and phi 2 at 10 kilohertz, then you will say give me a clock with 40 kilohertz and I'll get you phi 1 and phi 2. Likewise, if I just continue this argument, right, to 1 megahertz, right, you would say give me a clock of 4 megahertz and I'll give you for I'll give you a phi 1 and phi 2 at 1 megahertz, right. At the same time, now if I go to 1 gigahertz, right, 1 gigahertz is what, 10 power 9. So therefore this is going to be 1 nanosecond. Okay, I am now talking of 1 nanosecond, which means this has to be 4 gigahertz. And what does T clock of 4 gigahertz correspond to? It is going to be 250 picosecond. Okay, so fundamentally we see that yes, by making the clock faster and faster and faster, we can implement this sequential circuit requirement as needed. Okay, but clearly there is a limit up to which you can speed this up. Okay, and therefore before we just blindly say, yeah, you give me a clock which is 250 picosecond, I'll give you a phi 1 and phi 2 which can operate at 1 gigahertz, you must be very careful to find out if that circuit can operate at a clock period of 4 gigahertz in the first place. Okay, so therefore let's take one step back and let us analyze what is the maximum frequency at which this circuit can operate first of all. Okay, so therefore I am going to now make a copy of this. Okay, I am going to make a copy of this. Yeah, okay, and now I am going to ask you what is the maximum clock frequency at which this circuit will function correctly. Okay, so first of all you must understand that we have isolated the combinational blocks C1 and C2, right. The input and the next state logic and output logic are two different blocks. Okay, so in order to first of all find out the maximum clock frequency and all that, we need to redraw this in a slightly different way by combining C1 and C2 together. Okay, only then we will be able to even apply our analysis that we did in the earlier lecture, where we looked at, you know, the propagation delay of the combinational block, then we looked at setup, clock to Q delay and all that, and said you add all this, your clock period should accommodate at least this much delay, right. So therefore this is my C1 plus C2 and then I have my flip flops here. Okay, so okay, phi 1, phi 2 and I have phi 1, phi 2. Okay, so this is my clock, right. So now in order to do this, what I basically need is, so this is going to be my, so maybe I'll draw this out separately here because there are only two flops, it makes it easy. I'll just draw the clock like this. Right, so this is my clock, this is going to be my yeah. So what will happen is you are going to now replace this, this is my D, this is my Q, D and Q. Okay, So I'm going to take y0, y1, and so this is, let's say, y0, y1, okay, and I have d0, d1 here, okay. So what am I going to do? I'm going to first simply put an inverter between y0 and d0, right, and then I'm going to uh, put an other XOR gate, right, which is basically um, this one and this one, okay. This is my XOR gate. So let me call this I0, I'll call this X0, this I will call N0, and I1 and A0. Okay, these are my gates that I need to worry about. So this is I0, this is X0, and now what am I going to do? I am going to, so let me just replace this as phi 1 and no, I'll call this phi 2 and this as phi 1, okay. Now in order to get phi 1, I need to put a NOR gate, right, between y0 and y1, right. So this is my N0, right, and then what am I going to do? I'm going to invert y0, okay. I'm going to invert y0 and then pass it through an AND gate along with y1. Yeah, so this is my A0 logic, right? So I have 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. I have 5 gates represented here, right? So let me redraw this with little more space. So this is my I1 and this is my AND gate A0, okay. So effectively now what you can do is, you can see there is a combinational block that is sitting between flops, right. It's the same flop that is coming back in a cycle, right. So I can now look at the critical path or the propagation delay of this block, okay. So let us assume, okay, let us assume I will just redraw that circuit here slightly bigger, okay, so that it makes it easier. Okay, this is my y0, y1, and this is my d0, d1, and I have the, oh, this is a NOR gate, sorry, between y1 and, okay, so I have phi 1 here, and then I'm going to take y0, invert it, and then feed it to an AND gate. Yeah, Okay. So now what I'm going to do is I'm going to indicate the delays here. Okay, I'm going to say this is 100. All delays are in picoseconds now. Okay, I'm going to consider it. I'm going to consider the case in an IC. Okay, so typically a delay will be in the order of picoseconds. So 100 picoseconds. The NOR gate. Okay, I'm going to say that has a delay of XOR gate 300 picoseconds. Okay, the NOR gate 200. AND gate, I would say another 300, and inverter another 100. Okay, this is what I'm going to say is my delays. Now let's say that the inputs y1 and y0 arrive at t equal to 0, right? Then the arrival time at d0 will be 100 picoseconds. That is for the output for the input y0 to go through the inverter and stabilize to its final value. Likewise, y0 and y1 both arrive at t equal to 0. Therefore, you take the maximum of their arrival time, which is 0, and then add the delay through the XOR gate, which is 300. You will get 300 picoseconds here. Likewise, if you do the same thing for the NOR gate N0, right, phi 1 will stabilize after 200 picoseconds, right. Now, for the last thing, inverter I1 will allow the output to settle after 100 picoseconds, but the input to the AND gate, other input would have stabilized at 0. So therefore, the output of that AND gate will stabilize at maximum of the arrival times of the inputs, which is 100 plus 300 picoseconds. So this will be 400 picoseconds. Okay. So therefore, if you look at the critical path, you will pick the guy whose arrival time is largest and then go through the circuit which basically has the highest delay, and therefore this will be your critical path, right. And therefore, I can then say that the propagation delay TPD is about 400 picoseconds for this. Now, we know that when I put a combinational block between two flip-flops, the maximum clock frequency that you can operate this at is going to be the propagation delay plus the clock to Q delay of on the launch side and the setup time on the capture side, right. So if you remember, we looked at the idea of a flip-flop going through a combinational block. Okay, all controlled by the same clock. Okay, and we said that if this has to work correctly, your this is called the launch flop, and this is the capture flop. Okay, so the capture flop can become the launch flop for the next stage. If I have another combinational block after that, then the capture flop becomes the launch flop for that guy, right. But in any case, so the T clock out here should be greater than or equal to the TCQ of the launch flop plus the propagation delay of the combinational block plus the T setup of the capture flop, right. So now we'll assume here that TCQ is about I'll say another 200 picoseconds. T setup is also another maybe I would say to keep it simple, I would say this is, I'll just say another 200 picoseconds, it doesn't matter. Okay, let's just keep these numbers for now. And therefore, what this is basically telling us is that the T clock in this case should be greater than 800 picoseconds. That means anything less than 800 picoseconds, this system cannot work. Okay, and that's why when you came to 1 gigahertz and you said you wanted to generate phi 1 and phi 2 using this synchronous sequential circuit, you simply cannot. Okay, this is a limitation of sequential circuits. The clock frequency that we are talking about is limited to how fast you can make it operate, but there are conditions, there are circumstances where we need to generate clocks which are faster than this clock, the master clock that we are giving to this synchronous sequential circuit. Remember, I am telling you that this circuit can operate, you know, at a clock period which is greater than 800 picoseconds. But remember that the synchronous sequential circuit, the same clock will be going to many circuits, and the slowest circuit is what will determine your operating frequency. Therefore, this 800 picoseconds may well be like, you know, 1200 or 1500 picoseconds, right? So you may not be able to handle, you know, this kind of a design in a synchronous sequential circuit if you are operating at delays which are less than the minimum clock period which is allowed. Okay, and that's where something like asynchronous sequential circuits kick in.